Okay, so we're gonna have chapters 3, 4, and 5. I'll sort of summarize each of them, or not, I'm sorry, chapters 3 and 4. I'll summarize each of them, and then we can spend some time looking at some old test questions. But there are 14 multiple choice, but I'll count it like there's 15, so it's like there's one free question. And then there are 4 free response, and they are, uh, yeah, 4 free response. As I said in the email earlier, there's one that is projectile motion, there's one that's vectors, but it's also forces, but it's mainly a vector problem where you're just adding up vectors. And then there's another where you have an inclined plane with 2 bodies on it. Or we'll go through the procedure. We've done it in class, but I'll go through the procedure again on that. But you know, each one of them is a little bit different, so you just sort of have to follow that procedure and be flexible in it. And then the fourth free response problem is it's a 2D problem, but not on an inclined plane. So you have forces that are all different angles. Not many forces, just a couple. So let's see, what are we going to do first? Oh, so vectors. So with vectors, don't forget you'll need to do graphical plus numerical addition of vectors. So recall if we had like 2 vectors, A and B, like this is vector A, this is vector B. If I want to know A plus B, then I just draw A, and then I draw B. So this is A, this is B, and then the sum of those, I start at the beginning of A and go to the end of B. I always think of this in terms of displacement, right? Because if I start here, I end here. So I start either on the blue or the red here, and then I start on the blue, or I end at the end of the the path. If I want to take differences in vectors, so let's say I wanted to do A minus B, for example, first I would draw A, that is A, and then I would draw negative B. Remember, anytime I do a negative of a vector, I just switch its direction. Start at the beginning, end at the end. That is A minus B. I think there's one question, multiple choice, where you have to do graphical addition. You need to know basic stuff about vectors, like for example, where vectors lie in which quadrants. So for example, if I have a vector that has a positive x component and a positive y component, then that vector is in the first quadrant. If it has a negative x component and a positive y component, it's in the second quadrant, and on and on. Right, so if it was positive x, negative y, that would be which quadrant? It would be the fourth quadrant, right? So basic stuff about vectors. Look back at that concept test about vectors, and there are a number of questions there. Just sort of read through it. I think is that straightforward, the vector stuff? It sort of is. Some of them are kind of tricky, and you sort of got to be careful with them. Know what vector quantities are. Mass is a scalar quantity. Force is a vector quantity, that sort of thing. What's a vector? What's a scalar? I think y'all are okay on that. Let's see. You'll also need to know how to find the components. So, for example, if I have a vector that's 2 meters at 15 degrees, the x component of that vector is going to be 2 cosine 15. The y component is 2 sine of 15. You'll need to know how to add vectors, and this is one of the free response problems. It's sort of like the kite problem that we did in class. Y'all remember that problem where we had the squirrel with the kite, where we had 2 vectors, and we had to figure out what vector opposed it, what was the opposite vector. So let's say that we have a vector here and a vector here. We'll call this vector A, we'll call this vector B, and this is the angle theta. If I want to know the sum of those 2 vectors, A plus B, let's say that the sum is r is equal to a plus b. You first find the x and y components of each vector, you add them up, that gives you the x and y components of the resultant vector, and then you find the magnitude and direction by the angle. Listen guys, if I go too fast, there's a lot of material I want to sort of get through to cover, but if I am, just say, whoa, let's slow down, let's look at this more closely, okay? Is that clear? All right, so for example here, I like to make a little table, A, B, wait, no, that's not how I do it. A, B, x component, y component. So this would be A cosine theta. Actually, no, I'm sorry. Since A is along the x-axis, that's just going to be whatever the magnitude. Let's just give it some numbers. We'll say this is 2, this is 3, this is 20 degrees. So A would be 2 and 0. B would be 3 cosine 20, 3 sine of 20. You'd add up these to get Rx. You'd add up these to get Ry. And then to find the magnitude and direction of that, you'd say square root of Rx squared plus Ry squared. That's the magnitude. The direction is going to be the inverse tan of the y over the x. Ry over Rx. Yeah, Steve? Uh-huh. So it always helps to draw your vectors in this case. So I drew my vectors. This one was 2 units in the positive x direction, and then this was 3 units at 20 degrees from the positive x. So I know that the resultant of this vector is going to lie somewhere in between those vectors. I know that because I can do the graphical, right? I can take this vector and just sort of draw it over here, and then the resultant is going to be there. Just translate it over. So you just want to draw your picture. But for example, if I tell you, well, one of them is in the negative x direction, and then the other is 20 degrees below the negative x-axis, then in that case, I know that my x and my y component are both going to be negative. So it always helps to draw a picture. By the way, several times, 3 times on this test, I asked you to draw the free body diagrams. I think that you'll know how to draw them, and sometimes students don't draw them, but I'm thinking that it might help you to do better on the test. So just make sure that you're up on drawing your free body diagrams. Either drawing vector diagrams like this, where you draw vectors on a coordinate system, or on the Newton's laws problems, where you have to draw the forces and how the forces and how they're laid on a coordinate system. I haven't done that in the past, but I think that it will help you. Plus, it's just sort of some extra points that you can pick up because I think that people are generally pretty good at drawing those free body diagrams. But I will be looking for that, and just be prepared. I give you the coordinate systems. I say, draw the free body diagram. Not only that, but I ask you to resolve the vectors. So when you draw it, for example, you'll have your forces laid out. You would have something like Fn, Fw cosine of 30, Fw sine of 30. So you'll have your resolved vectors already laid out. I think that will help you when you get to actually solving the problem because you'll have it all there right in front of you. Okay? So vectors are sort of integrated all the way throughout because we do a lot of vectors. But it is also a separate problem, and there are like 3 or 4 multiple choice problems that are specific just to vectors, to chapter 3. Then we also have projectile motion. Again, there are probably 4 or 5 multiple choice questions about just projectile motion, the nature of projectile motion, and then we have 1 free response question that's a projectile motion problem. Let's see. There are like 3 to 5, I forget exactly, something like that. There are 14 total, so 3 to 5 of that, 3 to 5 of the projectile motion, and then the rest are Newton's laws. Would that be right? Yeah, 3 to 5 of each of those. Okay, projectile motion. How do y'all feel about projectile motion? You like it, I can tell. All right, there are really just 4 equations that we're dealing with. We have 2 equations that deal with projectile motion. It's our kinematics equations, v naught t plus 1/2 a t squared. By the way, there's no equation sheet on this test. You will have an equation sheet on the next test because all of a sudden we're going to get a lot more equations dealing with things. But right now we only have 4, so I don't really think it's that hard to memorize them. Well, it's not easy, but it just takes a little bit of time. We have these 2 equations, except they're specific to our projectile motion. We just add a subscript. All right, and then we also have similar equations for the x direction, where x is equal to vxt. It's made a lot simpler because the acceleration in the x direction equals 0, acceleration in the y direction equals -10 meters per second squared. Sort of our prototypical or stereotypical projectile motion problem, which you won't see one exactly like this, but it will help you to know how to work this. is where I have an object that is has an initial velocity at some angle. Remember, if you don't know the time, then you can always find the time by looking at the y velocity and realizing that the velocity in the y direction at the top of this trajectory is equal to 0. All right? So if I don't have the time, I can say, well, Vy top equals V naught plus AYT, and then solve that for T, top. Remember, whenever you have V naught, that this vector here is split into x and y components. I have a y component that's V naught sine of theta, and an x component that's V naught cosine theta. So I can say then that V naught y equals V naught sine of theta, and V naught x equals V naught cosine theta. That's right. My x is always cosine, my y is always sine. It's based on our definition of our trig functions. Of course, on the only caveat to that is with the inclined plane, we always take 90 minus the angle of the incline, but we'll get to that in a second. All right. Also, another thing that is useful here is that if this time at this point is t top, this time over here is twice t top. Your problem is very similar to this that you'll have like this. So make sure that you know this problem and how it works. But then also look at some of the other problems because it's a slight variation on this, okay? Which makes it more difficult. Well, that's all I can really say. All right? We'll look at some other projectile motion problems, but let's go on to the Newton's law stuff. So that's projectile motion. And then you'll have Newton's laws. In general, our procedure is to label the forces, just assess what are the forces all at play. And remember, the forces aren't always described, so you need to know what some of the forces are, just like the normal force, that's never described, but you know it exists. Likewise, the weight is there, and then if there's friction, then I'll say there's friction. If there's not, then I'll say it's no friction or whatever. If you have a question about that, you can ask me, and I can probably answer. Label the forces, draw a free body diagram. That's just that coordinate system with all of my forces on it. Again, this is going to be part of your problem, so you'll get credit for that. Also, resolve your vectors. And when you draw your free body diagram, I'll ask that you resolve the vectors on that free body diagram. And then the third step is apply Newton's second law. Sum of the forces in the x direction equals max. Sum of the forces in the y direction equals may. This applies for inclined planes as well as other problems as well with Newton's laws. You will have a two-body problem. Two-body problem works out exactly the same. I'll do like one we did in class. We did a couple in class. Yours won't be just like this, but it'll be similar, where you'll have two blocks, two bodies that are on or around an inclined plane, like this one. Right, usually these have different masses, M1 and M2. Need to be very, very careful with your subscripts on this, because that's really going to get you. So because this one's pretty straightforward, but if you have one that's slightly more complicated, like we worked one in class where you had a block that was up above the other, remember that one? In that case, we had two different blocks, two different frictions, and so if you didn't get your subscripts right, then it can throw you off. So you just take a big deep breath and say, I know how to do this, and make sure you get all your subscripts right. Okay. Fortunately, I give partial credit, so if you mess those subscripts up or if you get your equations slightly off, I won't count off a whole lot. But you want to get it just right. Like, I really prefer that you get the answer correct, because then it's a lot easier to grade. Okay? Because 100 is super easy to grade. Boom, 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 and you're done. Okay? All right. So you want to have two free body diagrams. Again, part of the problem is laid out for you. I ask you to do that. So you'd have a free body diagram for M1. Just label all your forces FT, FW1, recognizing that sometimes you have forces that are shared. So for example here, this FT is the same as this FT because it's the same rope. Anytime you have a rope or something connecting two blocks and there's a tension in it, it's going to be the same tension. All right, so notice I did not put a subscript there. On the second one, I can go ahead and label my forces. I have my normal force, and I'm doing my coordinate system, of course, like this. I have my normal force, which is parallel. I have my tension, and I have my weight. I have FW, let's say this is 30. It's going to be cosine of 60. This would be FW sine of 60. Go ahead and get pretty good at just going and resolving those in your head so you don't have to write it out. But if you want to write it out, that's fine. You would just put your force weight right here. This angle is 60 degrees, and then realize that I have x and y components on those axes. And then you apply Newton's second law. Now, if you have friction, you need to figure out, gosh, what direction is the friction? And then you say, well, what direction is it moving? And whatever direction it's moving, it's going to be opposite that. We don't know in this case. It depends on the mass of the blocks. Did I tell you that? Trying to think what the problem was like. Oh yeah, it's obvious. On the problem that I give you, it's obvious what direction they're moving. Okay. On some, it's not so obvious, but on the one that I give you, you'll know what direction it's moving. Either I tell you, or it's just you'll just see it. Okay. I read an article yesterday, and it said that when you're teaching a physics class, you should never use the word obvious because often it's not really that obvious. But trust me, you'll know what direction they're moving. Okay. You also shouldn't use straightforward or a lot of words that I use, unfortunately. So I'll try not to use those words anymore. Okay, so now I apply Newton's second law. I say the sum of the forces in the x direction. Looking at this one, that's FW cosine 60 minus FT equals MAX. Sum of the forces in the y direction, Fn minus FW sine 60 equals MAY. And then for the third one, FT minus FW1 equals MAY. Those are our equations, and then you can go through and ask yourself, what are the accelerations? Here, this acceleration is 0 because the block isn't moving up or down. It's stationary in the y direction. That's always going to be the case for your inclined plane. The acceleration in the y direction will be 0, but notice that this is not 0. And then you solve the equations. And you will have a system of two equations. I told you that in class. But you'll have two equations, two unknowns, and you'll need to solve that. The numbers are pretty simple, so the substitution isn't really involved, but it does require you to solve one equation for one variable and plug it into another. We've done several examples in class, but make sure that you can do that. If you want the extra 5 points credit, you can do the Gaussian elimination. If you feel like if at 7 o'clock tonight, you're like, man, I got this, I'm going to go to bed, just spend an extra half hour learning that Gaussian elimination. Just Google it. It's called Gaussian elimination. Or sometimes I think it's called like Gauss-Jordan elimination or something like that for solving a system of equations. So if spend half an hour, you could probably master it. Okay, so that's 5 points extra. All right, and that's it for the test. You want to look at some more questions? Do I have any particular ones that are bugging you? All right, look, I'm going to pull up some old tests, and we'll sort of scroll through them, and we'll see what we want to work. Let's start back at some of these that don't have solutions to them. Follow 5. Okay, so here's one. I have a stone that's thrown up onto a cliff as in this figure, And the initial velocity of the stone is 42 meters per second at an angle of theta naught equals 60 above the horizontal. And the stone lands at point A when t equals 5.5 seconds. So let's just sort of assess what I have here. I have that theta equals 42. 42 to, no, I'm sorry, that's not theta. Yeah, 60. I didn't bring my calculator. Um, I know that this is 42 meters per second. And I know that at this point, t equals 5.5 seconds. And that's all I really know, except, of course, I know that, I shouldn't say of course, but I do know that ax is equal to 0 and ay is negative 10. So those are never really stated, but we assume that they're true. And from those, our equations come. Let me just write down those equations. You know, you'll get that form, so if you want to write your equations on there, that's fine, just to sort of have in front of you. I have x equals vx times t, y equals v naught y t plus 1/2 ay t squared, and vy equals v naught y plus ay t. So those are my three equations. I want to know the height of the cliff. The height of the cliff, it's only a one-step problem. I just have to calculate the height of the cliff. I just take this, and I know everything in that except for the height of the cliff. The tricky part is knowing what time to use. I say, and I also need to know what v naught y is. That's 42 times what? For v naught y, to find my y component of the initial velocity. Sine of 60, that's right. Times t. Now what t do I use to find h? I want to know this height. No, not half the time. You don't have any idea? What is it? No, not t top. I want to know the y position right here. Do I know the time right here? It's 5.5 seconds. So that's what I'm going to use. At 5.5 seconds, this thing is right here. That's what it says in the problem. It lands at that point at 5.5 seconds. So if I want to know the height at that point, I just put in 5.5 seconds. Similarly, like if I want to know the range at that point, I would just put in 5.5 seconds for this equation, and that would tell me the x position. I can find the x or the y position at any time by using these different equations for the motion. All right, that's plus half of negative 10 is negative 5 times 5.5 squared. And that is what it is. I'm going to grab my calculator. I'll be right back. I'll be right back, y'all. Does anybody have that value? Don't worry about it if you haven't. It's not terribly important. It is what it is. Y'all can find that on your own. I'm going to close this, or clear this to go down to the next one. Here I want to know the x and y components of the velocity just before impact at point A. So if I want to do that, I just want to know what is the velocity here, both in the y direction and in the x direction. The x direction, the velocity in the x direction is really easy to get. It's equal to v naught x. Remember, in projectile motion, the x velocity doesn't change. It has an initial velocity in the x direction, and that's always the same. All right, so I just find v naught x, which is v naught times cosine of 60. That's 42 cosine of 60. And then if I want to find Vy, I'll know the x and the y components of the velocity. Vy, it's a little bit more complicated. I say V naught y plus ay times t. So that's going to be 42 sine of 60 minus 10 times, what time do I use? If I want to know the velocity in the y direction right here, what time do I use? I use that 5.5 seconds, right? So I say 5.5 seconds, and then that'll give me the y component of the velocity. And then in the next problem, part C, it asks for the magnitude and direction. So I have the x, I have the y. To find the magnitude of v, I just say the square root of vx squared plus vy squared. To find the angle, I say the inverse tangent of vy over vx. That's the opposite over the adjacent side. All right, that's a good problem. You could see one something similar to that. Okay, any questions about this one in particular? Did I clear this? You will not have to solve a system of equations for the projectile motion, so that does make it a little simpler, but it's still, sometimes students just have trouble with it. Don't worry about that. Let's look at some others. This was fall 05. Let's look at fall 06. That looks similar, but it's actually quite a bit different. We're going to skip that one. We had worked that in class, actually. Let's look at this inclined plane problem. Now, this one doesn't involve two bodies, but I think it'll be useful to look at regardless. Listen, we can come back and look at some more projectile motion problems after we work this one if y'all want to. But let's take a look at this. I have a crate of mass 200 kilograms pushed at a constant speed up a frictionless lamp by a horizontal force. What are the magnitudes of F and the force on the crate from the ramp? That would be like the normal force. So I want to know what is F and what is the normal force. It says that it's moved at a constant speed up that ramp. So that means that the acceleration in the x direction equals 0. Let me show you how that comes about. If I draw my coordinate system, always drawing it like this, this angle will be equal to this angle. Can you all see that? Do you see how that is? You have a line crossing two parallel lines, and so you have those similar angles. Let me see if I can draw it. It's sort of hard to see in this figure, but I have this line, and then I have this line, and I have this force. That's my force. Sorry, that's not working. My force cuts across those two lines. I'm drawing this line right here and this line, and this angle is 35. So that means this angle is also 35. You sort of see that? Is it, can you see it? Yeah, a little bit of geometry. I don't think you have complementary angles on your test, but nonetheless, it's sort of a useful thing to know for, life or whatever. Um, all right, so I draw my forces. I have one of the forces already labeled right there. Don't forget, I also have the weight, which is right here. This weight is at an angle of 90 minus 35, so that's, what, 55 degrees. And then I also have the normal force. And then those are the only forces. I can draw this on a separate coordinate system, which I'll ask you to do. Fn is right there. I'm going to go ahead and resolve my force weight. Fw cosine of 55, Fw sine of 55, and then I'm going to go ahead and resolve that other force vector, F. I'll do it in red. This is going to be f sine of 35, and this will be f cosine of 35. Notice that I did something here that normally with our inclined plane, right, this angle is 90 minus this. But notice here, this angle is 35. That's from the x-axis as it's drawn. So just be careful. You sort of have to know some geometry about the angles and what have you in order to work these. I think that y'all are pretty good at the geometry part. But let's see. So now I apply Newton's second law. But let's just first, I'm looking for F, and I'm looking for the normal force. So I can take a look here and see which of these axes can give me that answer. Well, if I'm looking for F, and I know that the acceleration in the x direction is 0, I can just solve it here. Look, you don't really have to write out the equations, especially if it's a static problem like this, or rather it's not a static problem, but it's a non-accelerating problem, because I know then that the forces on the x direction will have to add up to equal 0, and the forces in the y direction will have to add up to equal 0. So I can just look at this axis and say that f cosine of 35 equals fw cosine of 55. And then I can solve for f, because I know Fw, right? Fw is 2,000 newtons. I can just solve that for F. Once I find F, then I can find the normal force by looking at the y-axis. All right, I can say Fn equals Fw sine 55 plus F sine 35. I know F now. I know Fw. I just solve for Fn. Just calculate Fn. All right, that's an inclined plane problem. Let's look for one that has two bodies. They work really the same way, but usually you'll get a set of two equations with those. Can I clear this? Any questions, Steve? We might not have, no, but I it doesn't, yeah, you can see something like that. That's possible. Let's just take a second though, because it's not really much different from what we've been doing. Now the problem here that you're where you have this and this, you mean? Well, we have seen problems where we have opposite forces on the x-axis. Uh, I don't think that we've seen a problem where a force is in this direction, where it's horizontal to the ground or parallel to the ground. So the only difference here is that you just have to resolve this vector into its x and its y components. Um, but we have seen problems where we have forces on the negative and positive x directions, like when we have friction, for example. Anytime that something is either stationary or non-accelerating, you have that. You have to, in order to have a no net force in the x direction. Any problems with this? How we feel? How y'all follow this, sorta, kinda? Okay. Yeah, I didn't. I just sort of glossed over that, didn't I? So here, if you want to solve for, wait, can you repeat your question? Okay. So for f, you would find it here. So I have this f cosine 35 equals fw cosine 55. That comes about from here, where I know that these forces have to be equal but opposite because it's not accelerating. So the sum of the forces in the x direction has to equal 0. So this force minus this force has to equal 0. So these two are equal. So here I can solve that. I'll do it over here on the left where I have more space. If I solve for f, it's just going to be fw cosine 55 divided by cosine of 35. Now fw, I know the mass, and so fw is just equal to m times g. So that's going to be 200 kilograms times 10 meters per second squared. That's my g value. It's 2,000. But once you get fw and f, then you can plug it in here and you can find fn. Does that answer your question? Yeah. All right. Can I clear this one, yeah? I think that was it. Let's look for a two-body problem. That was follow 6. Generally, I wouldn't go this far back because sometimes, I don't know, my tests were, sometimes they were difficult, sometimes they were easy. I didn't really get consistent until about 2009 or so. This is still follow 8. We worked this problem in class, so let's see if I can find a different one. Okay, here we go. This one's similar to the one that we were looking at before, but it's made a little more complicated because it has friction. I have these two blocks. I know that they're accelerating. It tells me that it's accelerating in this direction. I can draw my coordinate systems here and here. I'll go and label my forces. I know this angle is 30 degrees. It says that in the problem. I know my forces. You know, boom, I got my force weight. I know I have to have that. That's FW2. I'm going to have FN2. I'm going to have my tension. Remember, the tension will be the same for both of these. And then I need to know also what is the direction of the frictional force. In this case, the direction of the frictional force is in this direction, Fk, because it's opposing the direction of motion. And I know it's going up the inclined plane. By the way, guys, sometimes you might have a problem where you don't know if it's moving. Like, for example, this is just a little aside, but it's important here. Well, it's not terribly important, but it's important that you know this. Let's say that I have an object, and I'm applying a force of 10 newtons, right? And I know that I have a certain coefficient of static friction here that is, I don't know, 0.3, and I know that the coefficient of kinetic friction is 0.1. Then I need to ask myself, is this object moving or not? It might be moving or it might not be moving. What would be the criterion to be if it's not moving? How would you determine if it's moving or not? If the kinetic is more than the static. Can you explain more what you mean? Okay, that's fine. You're sort of barking up the right tree, but you're not really saying the right words. Steve? Right. So let's say I have this object and I'm pushing on it with a force of 10 newtons. I could have a couple scenarios, right? I could have that 10 newtons is big enough to overcome the static friction, in which case it will move, or it's not big enough, in which case I'm just sitting there pushing and I'm not overcoming the static friction. So what you want to ask yourself is the static frictional force less than 10 newtons? If it is, it's moving. If it's not, it's stationary. It's not able to overcome that. So in this case, I know that my normal force, or I know that my weight, rather, here is 100 newtons. My normal force is also 100 newtons. My static frictional force, then, is going to be mu s times the normal force. So that's 0.3 times 100. That's 30 newtons. Is this object moving? Am I pushing hard enough with 10 newtons of force to overcome the static frictional force? Sure? So look, the static frictional force is 30 newtons. I'm only pushing with 10 newtons of force, so I'm not pushing hard enough. Uh, so could see a problem like that where I just ask you, is this thing moving or not? And that's really the question you want to ask yourself is, uh, am I pushing hard enough to overcome the static frictional force? And then you'll need to go through the process of determining what is the static frictional force. In order to do that, you have to know the normal force. You have to find the normal force. I'm sorry, that was a little aside, but it's an important aside. Uh, Now, in this problem, number 18, you know what direction it's moving, and you know that it is moving, uh, and I know what the coefficient of kinetic friction is too. Okay, so then I have a number of questions here. Let's go ahead and draw the coordinate system for block 2. I have Fn2, Fk, Ft, and Fw2 in the y direction. That's Fw2 sine of 60. And Fw2 cosine of 60. I want you to be at a good point right now so you can just throw out those vectors. Like you should look at an inclined plane and say, well, I know the direction of the weights. I know how to resolve those into the components. I don't even have to go through all this business on the left. I can just throw it up on the coordinate system and I see all those vectors. That's really the place you want to be before you go into the exam, that you can just look at it and see those vectors. If you're not quite there, that's probably going to be okay, but it just might take you a little more time. You're just going to be a little more crunched for time. So, okay, so if I want to find the normal force on block 2, this is my normal force on block 2, so I know that I'm going to be looking in the y direction. So I say the sum of the forces in the y direction, that's Fn2 minus Fw2 sine of 60 equals 0. So I know then that Fn2 will be Fw2 times sine of 60. That's going to be 0.5 times 10. That's 5 newtons. Sine of 60. Sine of 60 is a half, right? No, times 5. It's 4.3. So that's the normal force. If I want to find the frictional force, okay, that's just going to be mu times the normal force. It's 0.4 times 4.3. Mu was given up here. This is my normal force. So 0.4 times 4.3 is 1.7. And then what is the acceleration of block 2? If I'm going to find the acceleration, what do I need to consider, the x or the y motion? Okay, let's write out, right, I need to look at the x motion. Let's look at the sum of the forces in the x direction. I have Fw2 cosine of 60 plus Fk, I know what that value is, minus Ft equals m2a. And now let's ask myself, can y'all see that okay? See that writing? All right, so what do I know? Or let's just write what do I not know. I don't know the tension, and I don't know the acceleration. Don't know the acceleration. So I have two unknowns in that equation. So I need to find another equation. My other equation will come by the sum of the forces in the y direction on block 1. I have Fw1 and Ft. It's going to be Ft minus Fw1 equals m1a. And then I ask myself, what are the unknowns in that equation? I don't know Ft, I don't know a. So there's your system of two equations with two unknowns. You will have to solve such an equation. It won't be quite the same scenario as this, but a very similar thing. You see that two-body problem, you think, I'm going to have to solve a system of two equations. I'm going to have to substitute one equation into another. You want me to go through that here? Okay, so you want to just pick an equation. Well, we can make this simpler. Fw2 cosine 60. See, Fw2 was 21 newtons. Cosine 60, so that's 11 newtons. I'm rewriting this one up here. 11 newtons plus Fk. I've already found Fk. Where was it? Right here. 1.7 minus Ft equals m2, which was 0.5 times the acceleration. I'm going to solve this for the acceleration. And I'll solve it for Ft. Ft is equal to 13.7 minus 0.5 A. I've solved this for Ft. I'm going to take this now and plug it in right here, because that's equivalent to Ft. When I plug it into that equation, clear some of this stuff, I'm going to get something that looks like this. I'm going to get 13.7 minus 0.5A minus FW1. FW1 was 21 newtons. Okay, this is 2.1 kilograms. I just multiply that times 10. That's equal to M1, which is 2.1 A. Now notice I have only one unknown in that equation. So I can solve it. Get 13.7 minus 21 minus 7.3 equals 2.6 A. A is 7.3 over 2.6, negative 2.8. So that's the answer. Good thing too, because it comes out negative, and I was told in the very beginning that my acceleration was in that direction. If it wasn't, like, we got a problem, because back early on we decided that our frictional force was in this direction, and if it's accelerating the opposite direction, that means something went wrong, okay? So, like, something went wrong in my math somewhere along the way. Just be careful. Listen, with algebra, you just sort of got to take a big deep breath and take a lot of space to do it. Make sure your variables are all very clearly laid out. If you're not very neat, like I'm not a real neat person, if you're not very neat, try to lay out very clearly what you're doing, sort of keep all the steps in your head. If you need more paper, feel free. You can ask me to get some more paper. I can give you some. Oh, it should be 12.7. I'm sorry. I added these two numbers. Yeah, I'm sorry. Sometimes you'll make mistakes. If you make a mistake like that, I'll take off a point for a calculation error. Really be looking for those equations, looking for those free body diagrams laid out correctly, looking that your equations are laid out correctly. The algebra is important, but it's not terribly important. Y'all could do one of those, folks. You shall have a 2D two-body problem with a system of two equations. It won't be like this, but it'll be, a similar inclined plane. There are only so many variations of the inclined plane you can do. I don't think that I've given this particular problem ever on a test before, but you'll find similar problems to it on the test. Well, that's a mess, isn't it? Can I clear this? Don't do this, right? Just sort of be very neat about how you lay out your problem. Okay, can I clear this? If you need extra paper, please let me know. I'll try to give you more space. I feel like last time you were a little cramped for space. Huh? No, we didn't do this one in class. Maybe so. That's possible, yeah. All right. What else, y'all? I'm inclined to wrap it up, but unless y'all have particular questions. Oh, is it this problem? Right, so FW, remember, is m times g. So 2.1 kilograms times 10 meters per second squared, that's my g, is 21 newtons. Anytime, hey guys, anytime what I do, anytime I see a mass, I just go around and I say, well, that's 21 newtons. That's 5 newtons. Just move the desk. Multiply by 10. Right. Mm-hmm. Yep, you can go if you need. It's okay. Any other questions, y'all? Y'all class now? Okay.